Hello, friend. Welcome to Science for Sleep. Whether you've been here before or you're discovering this quiet corner for the first time, this is a place to slow down, learn something gentle, and let the day gradually settle away. Tonight, we are looking at something so familiar that it is easy to forget how strange it really is. Wood. A fence post can stand in a yard for years, then begin to soften and crumble right where it meets the soil. A deck board can turn grey beneath summer sunlight and winter snow. A roof beam hidden inside a dry building can remain strong for centuries. A wooden table protected indoors may pass from one generation to another with little more than scratches and faded varnish. And in archaeological sites, researchers sometimes uncover pieces of wood that have survived underground or underwater for hundreds, even thousands of years. All of these objects began as living plant tissue, yet they do not share anything close to the same lifespan. There is no single number that tells us how long wood lasts. The answer depends on what species of tree produced it, which part of the trunk it came from, how much water reaches it, how quickly that water can escape, whether oxygen is present, and which fungi, bacteria, or insects are able to reach it. Human choices matter too. A roof can protect a timber from rain. A preservative can make a fence post harder for fungi to attack. Simply keeping a piece of wood dry can sometimes preserve it far longer than choosing a naturally durable species and leaving it wet. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find this calm corner of science, one sleepy listener at a time. One useful distinction will make everything that follows much clearer. Wood that looks old is not necessarily wood that is rotting. Sunlight can slowly change the surface of exposed timber. Ultraviolet light breaks down some of the material near the surface, while rain washes away tiny altered particles. Over time, fresh brown wood may fade toward silver or grey. Small cracks, sometimes called checks, can open as repeated wetting and drying make the surface swell and shrink. Algae can leave green patches. Mold can create dark spots. Iron, reacting with compounds in certain woods, can cause black staining. None of these changes automatically means the deeper structure of the wood has been destroyed. True structural decay is different. In most familiar cases, fungi grow through the wood and begin breaking apart the material that forms its cell walls. Once enough of that microscopic framework is lost, the board can become soft, brittle, crumbly, or dangerously weak. But those fungi cannot simply attack whenever they please. They need several conditions at the same time. First, there must be wood they are able to use as food. Second, there must be enough moisture. Third, oxygen must be available. And fourth, the temperature must fall within a range where the organisms can remain active. Remove one of those conditions for long enough, and serious decay can slow dramatically or stop. That is why the base of a fence post is often more vulnerable than the part higher above the ground. Near the soil, water may remain available for long periods, while fungi and other organisms are already close by. It is also why a badly designed deck joint can rot, even when the surrounding boards look healthy. Water may collect inside a narrow connection and take much longer to dry than an exposed surface. A leaking roof can create the same problem in a hidden beam. The danger is often not that wood becomes wet once. It is that the wood stays wet long enough for biology to take advantage of it. The reverse can also be true. Dry interior timbers in old barns, houses, churches, and other buildings can remain useful for centuries because fungi never receive the moisture they need to keep growing. So decay is not a countdown that begins the moment a tree is cut down. It is conditional. A piece of wood lasts as long as its own structure, its chemistry, its surroundings, and the organisms around it allow. And to understand why one fungus can eventually turn a solid beam into fragile fragments, while another piece of wood remains almost untouched, we first need to look inside the material itself. Because wood is not one simple substance. It is an intricate biological structure built from several very different materials, each doing a different job inside the tree. A finished board may look like a solid piece of material, but its internal structure still carries the design of the living tree it once belonged to. Most of the wood inside a trunk is a tissue called secondary xylem. While the tree was growing, this tissue was produced by a very thin layer of living cells called the vascular cambium. The cambium forms a narrow ring just beneath the bark. As its cells divide, new bark-related tissue is produced toward the outside, while new xylem is added toward the inside. Year after year, those inward layers build most of the trunk we eventually recognize as wood. Under a microscope, that wood looks very different from the smooth surface of a table or floorboard. It is made from enormous numbers of tiny cells arranged mostly along the length of the tree. Many of those cells are much longer than they are wide. Their walls provide strength, while their hollow interiors once helped the tree transport or store water and other materials. The empty central space inside one of these cells is called a lumen. In living sapwood, water can move through these connected spaces and pathways from the roots toward the branches. The exact plumbing depends greatly on the type of tree. Softwoods, such as pine, spruce, and fir, rely heavily on long cells called tracheids. A single tracheid can help conduct water, while also supporting the tree mechanically. Water passes between neighboring tracheids through tiny openings in their walls called pits. Many hardwoods use a somewhat different arrangement. Oak, maple, poplar, and other flowering trees commonly contain larger tube-like structures called vessels. A vessel is built from many shorter cells joined end to end, forming a wider route for water to travel upward through the trunk. Some vessels are large enough to be visible with a hand lens on the cut end of woods, such as oak. These cells and tubes create the physical framework of wood, but most of their strength comes from the material forming their walls. One of the most important ingredients is cellulose. Cellulose is built from long chains of glucose molecules linked together. Thousands of these chains can gather into extremely small bundles called microfibrils. Those microfibrils run through the cell wall much like reinforcing fibers inside a composite material. Their arrangement gives wood much of its ability to resist being pulled apart along the grain. Around that cellulose framework are substances called hemicelluloses. Hemicelluloses are also made from chains of sugars, although their chains are shorter and more chemically varied than those of cellulose. They help connect different parts of the cell wall and interact closely with both cellulose and water. A third major component, lignin, helps give wood much of its stiffness. Lignin is a complex polymer made from smaller aromatic building blocks. In chemistry, aromatic refers to a particular ring-shaped molecular structure and has nothing to do with smell. As a tree forms mature wood cells, lignin is deposited through much of the cell wall and around neighboring cells. This material helps stiffen the structure and supports the tree against forces such as compression. That becomes especially important in a tall trunk, carrying the weight of thousands of branches and leaves. Cellulose, hemicelluloses, and lignin work together as a natural composite. Their proportions vary among species and even among different tissues in the same tree. A typical dry piece of wood contains a large fraction of cellulose and hemicellulose, with lignin making up another substantial part of its mass. That combination helps explain why wood can be light enough to float in many cases, while still supporting houses, bridges, furniture, and a living tree weighing many tons. It also explains why decay requires such specialized chemistry. A fungus trying to feed on wood has to reach material locked inside strong cell walls. Large cellulose molecules must be broken into smaller pieces. Hemicelluloses require their own enzymes and chemical pathways. Lignin presents an especially difficult barrier because its irregular molecular structure is resistant to many ordinary digestive enzymes. The strength of a wooden beam, therefore, depends on a microscopic arrangement built from millions upon millions of reinforced cells. When decay eventually weakens that beam, the process begins down at this scale. The cell walls lose the molecules that once allowed them to hold their shape and carry weight. Before fungi ever encounter those walls, however, a living tree has already changed some of them. As years pass and new wood forms closer to the bark, older wood deeper inside the trunk can enter a very different chemical state. That change creates the division between sapwood and heartwood, and it can have a major effect on how long the timber survives after the tree is gone. Close to the bark, much of a living tree's younger wood is still actively involved in the tree's daily work. This outer region is called sapwood. In a healthy tree, sapwood contains the pathways that carry water and dissolved minerals upward from the roots. It also contains living cells called parenchyma cells, which can store substances such as starch and help with chemical processes inside the trunk. Depending on the species and the age of the tree, sapwood may occupy only a few outer growth rings or extend much farther toward the center. A freshly cut pine log often shows this difference clearly. The sapwood near the outside may appear pale, while the older wood toward the center can be noticeably darker. That inner region is heartwood. Heartwood begins as sapwood earlier in the tree's life. As the trunk grows wider, the newest conducting wood continues to form near the outside. Older inner layers gradually stop taking part in water transport. In many species, the remaining living parenchyma cells in those older rings eventually die. Before and during this change, the tree can alter the chemistry inside the wood. Various compounds may accumulate within cell walls, cell cavities, and the tiny pathways that once carried water. These substances are often grouped together under the name extractives. Extractives are different from cellulose and lignin. Cellulose and lignin form much of the structural framework described earlier. Extractives are additional chemicals that can be removed from wood with substances such as water or organic solvents without destroying the main cell wall structure. Their chemistry varies greatly from one species to another. Some trees deposit resins. Others accumulate oils, gums, or compounds known as phenolics. Phenolic compounds are a large family of plant chemicals built around particular ring-shaped molecular structures. Many play roles in defense against microbes, insects, or physical damage. These compounds can also change what the wood looks and smells like. Black walnut develops rich brown heartwood. Western red cedar often has reddish-brown heartwood with a distinctive scent. Fresh teak can contain enough oily material to feel noticeably different from a dry piece of pale sapwood. Color alone does not tell us how durable the timber will be. But these visible differences often reflect real chemical changes inside the trunk. Some of those chemicals remain active long after the tree has been cut. They can slow fungal growth, interfere with insects, or make the wood a less suitable environment for organisms trying to feed on it. This helps explain why the heartwood of certain species has been valued for outdoor use. Western red cedar has long been used for shingles, siding, and outdoor structures partly because its heartwood contains compounds that give it useful natural resistance to decay. Teak became famous in shipbuilding and outdoor furniture for similar reasons, although its durability comes from a different chemical mixture. Black locust is another striking example. Its heartwood is naturally durable enough that it has traditionally been used for fence posts and other places where wood may remain close to damp soil. The sapwood from these same trees can behave very differently. Sapwood usually contains fewer protective heartwood extractives and remains more attractive to fungi and insects. A board cut partly from sapwood and partly from heartwood can therefore contain two zones with different natural resistance, even though both came from the same trunk. Heartwood itself still varies enormously among species. The dark center of a tree does not automatically mean the wood will survive outdoors for decades. Some species produce heartwood with relatively little resistance to decay. Others produce chemical mixtures that make fungal attack much more difficult. Tree age, growing conditions, and even position within the trunk can change the amount and distribution of these compounds. By the time a tree is harvested, part of its future durability has already been shaped by biological events that happened years or decades earlier. The tree formed new wood near its bark, moved older tissue inward, shut down its transport role, and gradually changed its chemistry while still alive. Once that timber leaves the forest, those internal differences begin interacting with the outside environment. Among all the conditions surrounding a piece of wood, moisture has an especially powerful influence. A naturally durable board may survive remarkably well when it stays dry, while a much more vulnerable piece can begin to change quickly if water remains inside its cells for long periods. To understand how decay truly begins, we have to follow that water into the wood itself. Once wood leaves the tree, it continues exchanging water with the air around it. This happens because wood is hygroscopic, meaning it naturally absorbs moisture from humid air and releases moisture when the surrounding air becomes drier. A board stored through a damp summer can gain water even when rain never touches it. The same board may lose part of that moisture during a dry winter indoors. These changes happen because the walls of wood cells contain chemical groups that attract water molecules. Some of that water becomes held within the microscopic cell wall itself. This is called bound water. As more moisture enters, the cell walls gradually swell. The change is small in any single cell, but across millions of cells it becomes large enough to make an entire board expand. That is one reason wooden doors can become tighter in humid weather and loosen again during a dry season. Eventually, the cell walls approach a condition called fiber saturation. Fiber saturation is the approximate point where the walls themselves are holding about as much bound water as they normally can, while most of the larger hollow spaces inside the cells still contain little or no liquid water. For many kinds of wood, this occurs somewhere around 25 to 30% moisture content. The exact number varies with species, temperature, and the wood's previous moisture history. Wood moisture content is measured in an unusual way. The mass of water inside the wood is compared with the mass the wood would have after being dried completely in an oven. A piece containing 30 grams of water for every 100 grams of oven-dry wood, therefore has a moisture content of 30%. Because water can sometimes weigh more than the dry wood itself, freshly cut timber can even have moisture contents above 100%. The important change for decay begins before the cell cavities are completely filled. Below roughly 20% moisture content, most ordinary wood decay fungi have great difficulty sustaining serious decay. Their cells need water to remain active, and the chemical reactions they use to break down wood also depend on moisture. As the cell wall becomes wetter, enzymes and smaller reactive compounds can move more effectively through the material. Fungal hyphae can remain active for longer periods, and the chemistry required to dismantle cellulose and other wood components becomes easier to maintain. Once moisture content rises toward roughly 30%, water is usually no longer the main thing holding decay back, provided oxygen and a suitable temperature are also available. Those figures are useful guides rather than hard biological switches. One fungal species may tolerate slightly drier conditions than another. Temperature changes the picture as well, and different woods hold water differently. Still, the practical lesson is remarkably consistent. Wood that remains below about 20% moisture content is usually at very low risk of sustained fungal decay. That helps explain why rain by itself does not doom an outdoor structure. Imagine a vertical cedar board on the side of a house during a summer storm. Rain may soak its surface for an hour. When the storm passes, sunlight, moving air, and gravity begin removing that water. The outer layers dry first, followed more slowly by moisture deeper inside. If the board repeatedly returns to a dry condition, fungi may never receive enough continuous wet time to establish serious decay. A hidden floor joist beside a leaking pipe can experience a very different future. Water may enter slowly and remain trapped where air movement is poor. Insulation or enclosed construction can slow evaporation. The joist may stay above the moisture range favorable to decay for weeks or months, even though no one ever sees standing water. Poorly drained deck joints create a similar problem. Two boards pressed closely together can trap rainwater between them. Their exposed faces may look dry the following afternoon, while the narrow space inside the joint stays damp much longer. The length of time wood remains wet often matters more than how dramatic the original wetting looked. This makes moisture almost like a gate controlling access to the wood's chemistry. Below the gate, fungal activity remains limited. As enough water enters the cell wall, the material becomes much easier for fungal metabolism to exploit. Yet water does not keep increasing decay forever. When wood becomes completely saturated and remains submerged, another requirement begins disappearing from the system. That requirement is oxygen. A damp beam inside a leaking wall can become a perfect place for decay. A timber resting deep beneath a lake can behave very differently. That contrast begins with oxygen. Most of the fungi responsible for familiar brown rot and white rot are aerobic organisms, which means they depend on oxygen to stay active. In an exposed board, oxygen is usually easy to find. Air moves through cracks, around surfaces, and into parts of the wood's internal pore system. Once enough moisture is present, fungal growth can continue because both water and oxygen are available together. Complete saturation changes that balance. When cell cavities fill with water and the surrounding soil or sediment remains soaked, air is pushed out of many of the spaces where oxygen would normally travel. Oxygen can still dissolve in water, but it moves through liquid far more slowly than it moves through air. That difference becomes especially important below the surface of mud. Microorganisms living near the top consume dissolved oxygen as they respire. If fresh oxygen cannot arrive quickly enough to replace it, deeper layers can become strongly oxygen depleted. A wooden object buried inside that sediment may remain wet all the time, while experiencing very little oxygen. Those conditions restrict many of the fungi that normally cause rapid structural decay. Brown rot fungi, which attack much of the cellulose and hemicellulose in wood, generally perform poorly when oxygen becomes severely limited. Many white rot fungi face the same problem. Their metabolism depends on oxygen-driven chemistry, including reactions used to attack lignin and other parts of the cell wall. This helps explain why archaeologists sometimes recover recognizable wooden structures from places where the material has remained saturated for centuries. Old waterfront pilings can survive below the waterline. Timbers can persist in lake sediments. Wood buried in bogs may remain visibly intact for very long periods. Shipwrecks can preserve large beams even after generations have passed above the water. The water itself is only part of the reason. The surrounding conditions often combine constant saturation with limited oxygen and, in many cases, low temperature. Cold environments slow chemical reactions and microbial growth. A timber buried in cold lake mud may therefore experience a much slower rate of biological change than a wet fence post sitting in warm summer soil. Depth can strengthen the effect. Sediment blocks water movement, oxygen becomes scarce, and temperatures may remain more stable than they are at the surface. The result can be a very unusual preservation environment. The wood remains wet enough to support life, yet the organisms best equipped for rapid decay may no longer dominate. Other organisms can take their place. Certain bacteria are capable of slowly attacking waterlogged wood. Some soft rot fungi can also function under conditions that limit the more familiar brown rot and white rot species. Their damage may progress over decades or centuries, rather than producing the rapid collapse seen in a warm, damp building. This is why underwater wood should never be thought of as frozen in time. Its chemistry can continue changing. Cellulose may gradually disappear from parts of the cell wall. Microscopic cavities can develop. A beam can preserve its outward shape while becoming weaker inside. The surrounding water may even help support spaces where solid material has already been lost. That distinction becomes extremely important when ancient timbers are eventually removed from the mud or raised from the seabed. For now, the main lesson is simpler. Wood decay depends on several conditions working together. Moisture can open the door for fungal activity, But extreme saturation can also reduce the oxygen those same fungi need. Temperature changes how quickly the remaining organisms work. Burial changes which organisms can reach the wood at all. The environment, therefore, decides much more than whether a piece of timber feels wet or dry. It determines which forms of life can actually use that timber as food. Once the right conditions come together near an exposed board, fungal spores already present in the environment can begin a much more active process. A microscopic filament emerges, enters the wood's internal structure, and starts turning a solid beam into a source of nutrients. Fungal decay begins on a scale far too small to see with the naked eye. Spores from fungi are constantly moving through forests, gardens, buildings, and outdoor air. They can settle on bark, fallen branches, fence boards, roof timbers, or freshly cut lumber. A single spore may be only a few micrometers across, meaning several hundred could fit side by side across the width of a millimeter. Most spores that land on wood never produce serious decay. The surface may be too dry. Temperatures may be unsuitable. The wood may dry again before growth can become established. When moisture and temperature remain favorable, however, a spore can germinate. A thin microscopic filament begins extending from it. This filament is called a hypha. Many fungal hyphae are only a few micrometers wide, yet they can continue growing through tiny spaces inside wood. As one hypha grows, it can branch repeatedly. Those branches form a connected network called a mycelium. The mycelium is the main feeding body of the fungus. The mushroom or bracket that may eventually appear on the outside is only the reproductive structure. Much of the organism can already be hidden inside the timber. Wood provides convenient routes for this growth because its internal anatomy was originally built to move water through a living tree. Hyphae can enter hollow cell interiors called lumens. They can pass through pits, the tiny openings that once allowed water to move between neighboring cells. Small cracks and exposed end grain can create additional roots into the material. From there, the fungal network can spread farther along the grain. This microscopic occupation does not immediately turn a strong board into soft rot. The fungus still faces a major problem. Most of the useful carbon inside wood is locked into very large molecules. A strand of cellulose can contain thousands of glucose units joined together. Those molecules are far too large for a fungal cell to simply pull inside and use. The fungus therefore digests much of its food outside its own body. Hyphae release enzymes into the surrounding wood. Enzymes are proteins that speed up particular chemical reactions. Some of these enzymes cut large carbohydrate molecules into smaller pieces. Once those fragments become small enough, the fungus can absorb them through the surface of its hyphae. Wood decay fungi can also release smaller reactive chemicals that travel into parts of the cell wall where large enzyme molecules have difficulty reaching. Together, these processes allow the fungus to begin dismantling material that may have supported the tree for decades. The strength loss can begin long before the wood looks dramatically rotten. Cellulose fibers start losing their original length and structure. Hemicelluloses can be broken apart. Changes inside the cell wall weaken the connections that once allowed millions of wood cells to act together as a solid beam. This is why visible mold and structural decay need to be treated as different things. Molds often grow on the surface when moisture is available and may produce dark, green, or pale patches. They mainly use simpler nutrients near the surface. The fungi responsible for serious wood decay possess chemical systems that can attack the structural material itself. Once those organisms become established inside a wet board, the appearance on the outside may reveal only a small part of what is happening deeper within it. A connected mycelium can continue exploring cell cavities while releasing digestive chemicals into nearby walls. Carbon that was once stored inside a tree becomes a source of energy for the fungus. The process is slow enough to be almost invisible from one day to the next. Yet over months or years it can change the strength of an entire timber. Different decay fungi accomplish this with surprisingly different chemical tools. Some specialize in stripping away much of the cellulose and hemicellulose while leaving a dark residue rich in altered lignin. Others possess the rare chemistry needed to attack lignin itself. Those different strategies produce forms of decay that can look, feel, and behave very differently inside the same basic material. One of those strategies produces a familiar pattern called brown rot. Wood affected by severe brown rot often becomes darker and much more fragile than sound timber. As the damage progresses, the wood can shrink and develop cracks that run both along and across the grain. Those cracks may divide the surface into rough, block-like pieces. This pattern is often called cubical checking. A badly decayed piece may still resemble the board or beam it once was, even though a gentle squeeze can make parts of it crumble. The brown color comes partly from what the fungus leaves behind. Brown rot fungi attack the carbohydrates that make up much of the wood cell wall, especially cellulose and hemicelluloses. They remove relatively little of the lignin. The remaining lignin is chemically changed during decay and becomes concentrated as other parts of the wood disappear. That altered, lignin-rich material gives advanced brown rot much of its characteristic brown appearance. The loss of cellulose has an especially serious effect on strength. Cellulose molecules form long chains that gather into the microfibrils running through the cell wall. Those microfibrils help wood resist pulling forces along the grain. When a brown rot fungus begins shortening and breaking those cellulose chains, the cell wall can lose strength surprisingly early in the decay process. A timber, therefore, does not have to look completely rotten before its mechanical performance has changed. Researchers studying brown rot have spent considerable time working with a species called Postea placenta. This fungus is commonly used as a laboratory model because it can decay softwood efficiently and gives researchers a clear view of the chemistry involved. Softwoods, such as pine and spruce, are especially important habitats for many brown rot fungi. In northern forests, brown rot plays a major role in breaking down fallen conifer trunks. The fungus faces a physical problem when decay begins. Many of the enzymes capable of cutting cellulose are large molecules. They cannot easily enter every narrow region inside an intact wood cell wall. Postea placenta and other brown rot fungi begin solving this problem with much smaller reactive chemicals. One important process involves iron and hydrogen peroxide. Together, under the right chemical conditions, they can produce highly reactive molecules called hydroxyl radicals. A radical is a molecule or part of a molecule that reacts very readily with surrounding material. These tiny reactive compounds can move into portions of the cell wall that larger enzymes cannot initially reach. They begin disrupting cellulose and hemicellulose from within the structure. As the wall becomes more open and chemically altered, fungal enzymes gain better access to the damaged carbohydrates. The larger molecules can then be broken into smaller pieces that the fungal hyphae can absorb and use. This combination gives brown rot an unusual speed during the early loss of strength. The wood may still hold its general dimensions, while cellulose chains have already been shortened dramatically. Tests of brown rotted timber have shown that important strength properties can decline well before a large percentage of the wood's total mass has disappeared. That matters in buildings because a beam can look much more intact than its internal condition would suggest. The same process explains the brittle texture of advanced brown rot. Once enough carbohydrate material has been removed, the remaining lignin-rich framework cannot carry loads the way the original composite cell wall could. Drying then causes the weakened material to shrink. Cracks widen across the damaged cells, producing the blocky patterns seen in old rotten logs and severely decayed structural timber. In a forest, this chemistry helps return the carbon stored inside fallen trees to other living organisms. Inside a damp building, the same fungal machinery can slowly remove the strength from a joist or beam. Brown rot succeeds by attacking much of the carbohydrate framework while leaving a large share of the lignin behind. Lignin is one of the most chemically difficult parts of wood to dismantle. Certain fungi possess a different set of enzymes that allows them to break through that resistant material as well. Some decayed wood takes on a very different appearance from the dark, blocky remains left by brown rot. It may become pale, fibrous, or stringy. In advanced cases, the wood can look almost bleached. This pattern is usually associated with white rot fungi. Their chemistry reaches one of the toughest parts of the wood cell wall, lignin. Lignin helps stiffen wood and surrounds much of the carbohydrate framework formed by cellulose and hemicelluloses. Its molecular structure is irregular and heavily cross-linked, which makes it difficult for many organisms to break apart. White rot fungi possess unusually powerful oxidative systems that can overcome that resistance. Several important enzymes are involved. One is called lignin peroxidase. Another is manganese peroxidase. Peroxidases are enzymes that use compounds such as hydrogen peroxide to drive highly reactive chemical reactions. Those reactions can begin breaking the complex bonds inside lignin. Some white rot fungi also use enzymes called locusts, which help oxidize a wide range of plant compounds. The exact mixture differs among species. A well-studied white rot fungus called Phanerochaete chrysosporium became especially important in research because of its ability to produce lignin-degrading peroxidases. Its enzymes help scientists understand how fungi accomplish something most animals and bacteria cannot do efficiently: dismantle large amounts of lignin. White rot does not always remove every part of wood at the same rate. Some species attack lignin, cellulose, and hemicelluloses together. Others remove lignin more selectively at certain stages, leaving lighter-colored cellulose-rich material behind for a time. That difference helps create the pale or fibrous texture often seen in white-rotted logs. The result can be very different from brown rot, even though both fungi began with the same basic material. A fallen branch affected by brown rot may eventually break into dry, dark cubes. Another log colonized by white rot fungi may separate into pale fibers that can sometimes be pulled apart by hand. There is also a third major pattern called soft rot. Soft rot fungi often belong to a large fungal group called the Ascomycetes. Many of the classic brown rot and white rot fungi belong instead to another group known as Basidiomycetes, which includes many familiar mushrooms and shelf fungi. Soft rot becomes especially important in environments where ordinary decay fungi struggle. Persistently wet timber, cooling towers, wooden utility structures, and waterlogged material can all provide suitable conditions for certain soft rot species. Their microscopic damage follows its own pattern. Some soft rot fungi grow inside the wood cell wall and create long cavities within it. Under a microscope, these cavities may appear as narrow channels running through particular layers of the wall. Other soft rot fungi erode the wall gradually from the cell cavity inward. The damage can progress slowly, but over enough time it still removes structural material. These categories are useful because they describe recognizable patterns. Modern genetics has also shown that nature does not always respect the boundaries humans draw around them. Scientists comparing fungal genomes can look for genes involved in enzymes that attack cellulose, hemicellulose, and lignin. Some species carry combinations that resemble a typical white rot toolkit. Others have lost many lignin-degrading enzymes and behave more like brown rot fungi. A few sit somewhere between those familiar patterns. This suggests that fungal decay strategies changed gradually through evolution. Lineages gained, modified, or lost parts of their chemical machinery over millions of years. Brown rot, white rot, and soft rot are therefore useful descriptions of major strategies within a much wider range of fungal biology. The important result is that dead wood faces several different kinds of chemical attack. Some fungi reach the carbohydrates quickly. Others can dismantle lignin itself. Certain species operate in wet conditions that limit many of their competitors. With so many roots into the same cell wall, the survival of naturally durable timber begins to look even more remarkable. Its advantage often comes from compounds the tree placed inside the wood, long before any fungal spore arrived. A fungus entering one species of wood can encounter a very different material from the one it would find in another. Even boards that look similar from a distance may vary greatly in how easily they decay. Western red cedar is a good example. It is a softwood from a conifer, yet its heartwood can resist fungal decay far better than the wood of many other softwood species. That durability helped make Western red cedar useful for shingles, siding, outdoor furniture, and other places where timber regularly faces moisture. Redwood shows a similar pattern. The heartwood of mature coast redwood can contain natural compounds that slow decay, which contributed to its historical use in outdoor structures across Western North America. Teak provides an example from a very different part of the world. Native to South and Southeast Asia, teak has been valued for centuries in shipbuilding, furniture, and exterior construction. Its heartwood combines useful stability with natural resistance to many organisms that attack wood. Black locust, a tree native to eastern North America, produces another famously durable heartwood. Its timber has traditionally been used for fence posts, stakes, and other ground contact applications where ordinary untreated wood may deteriorate much sooner. These examples can make it tempting to sort wood into simple categories. Hardwood sounds as though it should mean strong, dense, and durable. Softwood sounds as though it should mean the opposite. Those names actually describe the trees that produce the wood. Hardwoods come from angiosperms, the flowering plants that include oak, maple, walnut, poplar, and balsa. Softwoods generally come from gymnosperms, especially conifers such as pine, spruce, fir, and cedar. The terms say very little by themselves about physical hardness. Balsa demonstrates this clearly. Balsa comes from a flowering tree and is therefore classified as a hardwood. Its dry wood can be extraordinarily light and soft compared with many conifers. At the other end of the scale, some softwoods can be quite dense and mechanically strong. Botanical family also tells us little about decay resistance. Western red cedar is a softwood with naturally durable hardwood. Many pines are also softwoods, yet untreated pine sapwood can decay readily when it remains wet. Among hardwoods, teak may last for many years outdoors under favorable conditions, while poplar is generally much less resistant to fungal decay. Density creates another misleading shortcut. Dense wood often feels stronger in the hand, and density can influence many mechanical properties. Fungi are responding to much more than weight. A heavy piece of wood can still contain cell walls and nutrients that decay organisms can use efficiently. A lighter species may contain chemicals that interfere with fungal growth. This is why two woods with similar density can have very different service lives outdoors. The exact part of the tree matters as well. A durable species does not produce equally durable material across the entire trunk. The pale sapwood surrounding the hardwood usually contains fewer of the protective chemicals associated with natural durability. Sapwood also served as active transport and storage tissue while the tree was alive. Once the tree is cut, that material can provide fungi and insects with a much more favorable environment. A plank of cedar or teak containing a large band of sapwood may therefore behave differently from a board cut almost entirely from mature heartwood. Even within the heartwood, durability exists on a range. One species may slow fungal attack moderately. Another may remain resistant for much longer under the same conditions. Differences in anatomy contribute to that performance, including how easily water can travel through the cells. Chemistry often explains an even larger part of the contrast. The extractives formed during heartwood development can remain inside the timber for decades after the tree is cut. Some interfere directly with fungal cells. Others affect the chemical reactions fungi use to break down wood. Their amount and composition can differ sharply between cedar, teak, redwood, black locust, pine, and poplar. That means the apparent toughness of a board tells only part of its story. Much of its natural resistance may come from a relatively small collection of compounds hidden within the cell walls and cavities. Those compounds are the reasons some fungi find one heartwood difficult to colonize, while another piece becomes a much easier source of food. The protective advantage of durable heartwood often comes from chemicals present in surprisingly small amounts. Most of a board is still built from cellulose, hemicelluloses, and lignin. Extractives occupy a much smaller share of the material, yet they can strongly influence how that wood smells, how it responds to water, and how easily fungi can grow through it. The name extractive covers a wide range of chemicals rather than one substance. Some belong to groups called phenolic compounds. Others include quinones, tannin-related molecules, resins, oils, and terpenoids. Terpenoids are plant chemicals built from small carbon-based units, and many contribute to the familiar scents of cedar, pine, and other trees. Each species produces its own mixture. Western red cedar heartwood contains compounds called thujaplitins. These belong to a group of chemicals known as tropolones, and can inhibit the growth of several wood decay fungi. They contribute to the natural durability that made cedar useful for shingles and outdoor structures. Teak hardwood contains a different collection of compounds. One of them is tectoquinone, a quinone that has been associated with teak's resistance to fungi and termites. Black locust relies on yet another chemical mixture, including flavonoid compounds found in its highly durable heartwood. These molecules do not all protect wood in the same way. Some are directly toxic to fungal cells at sufficient concentrations. A fungus trying to colonize the heartwood may grow more slowly, produce fewer active hyphae, or fail to establish itself efficiently. Other extractives interfere with the chemistry fungi use to digest the cell wall. Brown rot fungi, for example, depend partly on reactions involving iron and highly reactive oxygen-containing molecules. Certain heartwood compounds combine metals or act as antioxidants. An antioxidant is a substance that can reduce some of the highly reactive chemical reactions that damage nearby molecules. Inside durable wood, this may interfere with part of the chemical system a fungus uses to open the cell wall. Other compounds can affect fungal cell membranes or interfere with enzymes. The result comes from several small obstacles acting together. A fungus may face slower growth while its digestive chemistry also becomes less effective. Water movement through the wood may change as well, especially when oily or resin-like substances occupy parts of the cell structure. Researchers can test the importance of these chemicals by removing them. A piece of naturally durable hardwood can be ground or cut into samples and treated with solvents that dissolve particular extractives. The structural cellulose and lignin remain, while part of the protective chemical mixture is washed away. When the treated wood is later exposed to decay fungi, it can lose substantially more mass than untreated heartwood from the same species. Similar experiments involving termites have produced greater feeding damage after certain protective extractives were removed. That result is important because the tree itself has not changed species. The basic cell walls are still present. Much of the difference comes from a relatively small chemical fraction that had been stored among those walls. Natural durability also depends on concentration. Heartwood, near one part of a trunk, may contain a different amount of a protective compound than wood from another part. Trees growing in different regions can produce somewhat different chemical profiles. Some extractives slowly evaporate, oxidize, or wash from timber during years of outdoor exposure. A species known as durable, therefore, still has limits. There is no universal substance that can simply be called the chemical that stops wood from rotting. Western red cedar, teak, redwood, and black locust reach useful durability through different combinations of compounds. Their protection comes from interactions among fungal toxicity, antioxidant effects, moisture behavior, and other chemical properties. A relatively small amount of material can therefore influence the fate of an entire beam. That chemistry becomes even more interesting when we consider where those compounds sit. Water still has to enter the wood. Fungal hyphae still have to spread through its internal pathways. Preservatives applied by humans face many of the same roots and barriers. The vessels, pits, cell cavities, and grain that once carried water through a living tree continue controlling movement long after the trunk has been turned into lumber. The pathways inside wood still behave a little like the plumbing of the living tree that built them. This becomes especially clear when water reaches a freshly cut surface. A board can absorb liquid much more easily from its cut end than through a broad face. The reason lies in the direction of its cells. Most wood cells run lengthwise from the roots toward the crown. Once the tree is cut into lumber, those same long pathways usually run along the grain. This gives wood a property called anisotropy. Anisotropic simply means that a material behaves differently depending on direction. Wood can differ by direction in strength, shrinkage, heat movement, and the way liquids travel through it. For moisture, the contrast can be especially large. Water can often move far more easily along the grain than directly across intact cell walls. The end of a board exposes thousands of small openings that once formed parts of the tree's transport system. Rain touching that end grain can therefore enter much deeper than the same amount of water landing on a smooth side surface. This is one reason exposed ends of deck boards, fence rails, and outdoor timbers can become vulnerable when they remain wet. The exact pathways depend on the kind of tree. In hardwoods, such as oak, ash, or maple, many of the most obvious water channels are vessels. These are tubes made from cells joined end to end. In ring-porous woods such as oak, some vessels formed early in the growing season can be wide enough to see as tiny openings on a cleanly cut surface. Softwoods, such as pine and spruce, are built differently. They generally lack those large vessels. Most water movement occurs through long cells called tracheids. Neighboring tracheids connect through microscopic structures called pits. These pits act as small passageways between cells and helped water move upward while the tree was alive. After the tree dies, some of these roots become harder to use. In many softwoods, parts of the pit structure can shift and seal. This process is called pit aspiration. It reduces the ease with which liquid can pass from one trachid to another. Hardwood formation can add further barriers. Extractives may collect in cell cavities or around pits. Some pathways become blocked as the inner wood ages. Hardwoods can develop their own type of blockage. White oak provides a useful example. Its vessels commonly contain structures called tyloses. A tylosis forms when a nearby living cell pushes a balloon-like growth into the vessel and partially or completely blocks it. These blockages help make white oak hardwood relatively difficult for liquids to penetrate. That property has practical consequences. White oak became well known for uses such as barrels and boat building because its vessel system is comparatively tight. Red oak, although closely related, often has much more open vessels. Air can sometimes be blown through a short piece of red oak along the grain with surprising ease. Those anatomical differences affect more than water. They also influence how fungi spread and how deeply preservatives can enter. A preservative placed on the surface of a permeable sapwood may travel through open pathways with relative ease. Dense or heavily blocked hardwood can resist penetration even when pressure is applied during treatment. This creates an interesting problem for wood preservation. Some hardwoods already contain natural chemicals that make them harder for fungi to attack. Those same tissues may also be difficult to treat deeply with added preservatives because their internal pathways are partly closed. Sapwood often behaves in the opposite way. It usually contains fewer natural protective extractives, but its transport system can remain much easier for liquids to enter. That is why two pieces of lumber from the same species can accept treatment very differently, depending on where they came from inside the trunk. Grain therefore tells a deeper story than surface appearance. Its direction reflects the alignment of cells. Its pores reveal old water pathways. Its blocked vessels and closed pits record changes that happened while the tree was still alive. Once that wood becomes lumber, those features continue influencing where moisture enters, how fungi spread, and whether human treatments can reach the places that need protection. Because this structure was grown by a living organism, rather than manufactured from a fixed recipe, no two trees produce perfectly identical wood. Even boards carrying the same species name can begin their useful lives with meaningful differences already hidden inside them. Two boards sold under the same species name can carry very different histories inside them. A piece of coast redwood from a young tree, for example, may behave differently from timber cut from a much older redwood. Even two boards taken from opposite parts of one trunk can contain different amounts of heartwood, protective extractives, and younger wood formed early in the tree's life. The variation begins near the center of the trunk. During a tree's first years of growth, the cambium produces what wood scientists call juvenile wood. This early wood forms close to the center and often has different cell dimensions and internal structure from the mature wood produced later. As the tree becomes older and wider, the characteristics of newly formed wood gradually change. The transition takes place over a number of growth rings rather than at one sharp boundary. Heartwood adds another layer of variation. In many species, the proportion of heartwood tends to increase as a tree grows older and its trunk becomes wider. A large mature tree may therefore contain a substantial central region of heartwood, while a younger tree of the same species can contain a greater proportion of sapwood. That matters when the heartwood carries much of the species' natural resistance to decay. Coast redwood provides a useful example. This species, Sequoia sempervirens, can live for well over 1,000 years along the Pacific coast of North America. Its heartwood has long been valued for natural decay resistance. Studies of redwood have also found considerable variation within the species. Young growth redwood has generally shown lower decay resistance than heartwood from old growth trees, and even the heartwood inside individual trees can vary in durability. The difference appears to be connected partly to extractives. These protective chemicals are deposited as sapwood becomes heartwood, often years after the growth ring itself first formed. Their concentration and exact mixture can vary with location inside the trunk and between individual trees. Growth conditions can influence other wood properties as well. A tree growing on a fertile site with abundant light may add wide growth rings relatively quickly. A crowded tree receiving less light may grow more slowly. Plantation forestry can encourage rapid diameter growth through spacing, thinning, and site management. Faster growth can change the proportion of juvenile wood present in a harvested log, although the effect on strength or durability depends heavily on the species. Teak shows a similar reason for caution when broad labels are used. Natural teak forests have produced timber famous for durability, while modern teak is also grown in plantations across tropical regions far beyond its original South and Southeast Asian range. Young plantation trees can contain a relatively large share of sapwood and younger heartwood. The chemical protection inside teak also changes with age and position. Experiments using heartwood from 20-year-old teak have shown that its extractives can affect termite feeding, demonstrating that the protective chemistry is already present in relatively young material even though its performance should not simply be assumed identical to hardwood from much older trees. This is where claims about old-growth lumber need some care. Older trees can provide more mature wood, and, in certain species, a larger proportion of highly durable hardwood. Redwood offers real evidence for such a difference. That does not create a general rule that every old tree produces stronger or more decay-resistant lumber than every young tree. Species biology, growth conditions, defects, extractive chemistry, and the exact part of the trunk all influence the final material. Natural durability ratings therefore describe typical behavior. They cannot promise the lifespan of one particular board. A piece of cedar may begin with unusually protective hardwood chemistry, while another cedar board contains more vulnerable sapwood. Two redwood timbers may differ in extractive content, even when their labels at the lumberyard are identical. Wood carries the record of a living organism, whose cells developed over decades or centuries under changing conditions. Those differences help determine how well the material can resist fungi once the tree is gone. Even unusually resistant timber eventually meets a stronger influence if its surroundings remain favorable to decay. A durable board that stays damp for weeks at a time gives fungi an opportunity that a less durable board kept consistently dry may never provide. A board can begin with excellent natural durability and still fail if one small part of it stays wet for too long. The important environment is often very local. Wood scientists sometimes use the word microclimate for the temperature, moisture, airflow, and exposure found in one small place. Two ends of the same timber can live in different microclimates only a few meters apart. One end might face open air and dry quickly after rain. The other may sit inside a shaded joint, where moisture remains trapped for days. Ground contact creates one of the harshest conditions. A wooden post buried in soil is surrounded by a material that can hold water long after the surface appears dry. Soil also contains fungi, bacteria, insects, and other organisms already adapted to breaking down plant material. Near the surface, enough oxygen can still reach the wood to support many decay fungi. That combination of moisture, oxygen, and biological activity makes the wood-soil boundary especially demanding. For this reason, ground contact tests are commonly used when researchers compare the durability of different woods or treatments. Stakes are placed partly into soil and left outdoors for years while their condition is checked. The exposure is intentionally severe. The buried portion stays damp much longer than a board hanging freely in the air. Buildings create their own small wet zones. A roof may look sound from outside, while a failed piece of flashing allows rain to enter around a chimney. Flashing is a thin layer of metal or another waterproof material that directs water away from joints. If it fails, water can run into spaces where sunlight and moving air never reach. A wooden rafter inside that cavity may stay damp long after the roof surface has dried. Wet insulation can make the situation worse by holding moisture against the timber. Decks have similar weak points. A flat board exposed to rain can dry reasonably well when air reaches both sides. Water trapped between two tightly connected boards may remain much longer. Screws, bolts, and overlapping pieces can create tiny pockets where liquid collects. Horizontal surfaces usually dry more slowly than vertical ones because gravity cannot remove water as easily. End grain can add another pathway, drawing moisture along the internal cells of the wood. Paint can sometimes hide the damage. A painted window frame or exterior trim board may look intact while decay develops underneath. If water enters through a crack and the coating slows evaporation, the outer surface can remain smooth, while the inner wood loses strength. By the time softness or cracking becomes visible, fungal activity may have been present for a long period. Temperature affects how quickly that activity proceeds. Many common wood decay fungi grow efficiently at temperatures close to those found in comfortable indoor spaces or warm summer weather. For many species, conditions around 21 to 32 degrees Celsius support strong growth when moisture and oxygen are already available. Colder temperatures slow metabolism. Very high temperatures can also reduce growth or kill fungal tissue, depending on the species and how long the heat lasts. Temperature usually acts as an accelerator once the wood is wet enough. A dry beam at 25 degrees Celsius can remain stable because the fungus still lacks sufficient moisture. A damp beam at the same temperature may provide nearly ideal conditions. This helps explain why rainfall alone is a poor way to predict decay. A vertical wallboard might receive heavy rain several times each month and still dry rapidly between storms. A hidden timber beside a slow plumbing leak may receive far less water overall, yet remain continuously damp. The second piece can be at much greater risk. Time of wetness often controls the outcome. A naturally durable species can eventually be overwhelmed when it remains in a favorable fungal environment for months or years. An ordinary species may survive for generations when its moisture stays below the range needed for sustained decay. That principle shaped wooden buildings long before anyone knew what fungal hyphae looked like under a microscope. Builders learned through experience that timber lasted longer when rain was shed away, soil was kept at a distance, and damp spaces were given a chance to dry. Much of the oldest surviving wooden construction depends on those simple physical choices. Long before builders could measure moisture content with an electronic meter, they had already learned one of the most useful rules in wooden construction. Timber lasts much longer when water is given a clear way to leave. Traditional buildings often reveal that lesson in their shape. Wide roof eaves extend beyond the walls and reduce the amount of rain striking wooden siding, window frames, and structural joints. A roof with a generous overhang can keep large areas of wall dry even during a heavy storm. Stone foundations served another practical purpose. By raising timber frames above wet soil, builders reduced direct contact with one of the most aggressive environments for decay. The stones carried the weight of the structure while separating wooden posts and beams from ground moisture. This principle appears in many forms of traditional construction. Wooden buildings may rest on masonry walls, stone piers, or raised foundations that allow air to move beneath the floor. The exact materials vary, but the physical goal remains the same. Water should drain away before it stays inside the wood long enough for fungi to become established. Modern buildings use more specialized details to accomplish this. Flashing is one of the most important. A piece of flashing is usually a thin sheet of metal, plastic, or waterproof material, positioned so that rain is directed over a joint instead of into it. Flashing can be found around windows, beneath roof edges, beside chimneys, and where decks connect to buildings. Its shape uses gravity to move water toward the outside. Small mistakes can have large consequences. A gap of only a few millimeters can become a pathway for rain if water is able to enter repeatedly. Narrow spaces create another problem through capillary action. Capillary action allows water to move through very small gaps, sometimes even against gravity. The effect comes from the attraction between water molecules and the surfaces surrounding them. Two boards pressed tightly together can create a narrow space that draws water inward and holds it there. A capillary break interrupts that path. Builders may create a wider gap, add a waterproof layer, or shape materials so that water cannot continue traveling through the joint. Ventilation deals with moisture that does get inside. A wall cavity with some airflow can release water vapor as conditions become drier. A ventilated roof space can do the same. Moving air carries moisture away from surfaces and helps wet wood return toward a safer moisture level. This is why successful wooden construction does not require every board to remain perfectly dry every minute of its life. Rain can reach siding. Humidity can rise during summer. Small amounts of moisture can enter a building assembly. The important factor is how long that moisture remains. When wood can repeatedly dry below roughly 20% moisture content, sustained fungal decay becomes much less likely. A timber that becomes wet for a few hours and then dries may remain sound for many years. A similar timber trapped above the decay range for weeks at a time faces a much greater risk. This idea helps explain the survival of many old wooden buildings. Some historic beams have lasted for centuries because roofs kept most rain away, while foundations separated them from damp ground. Their survival may have depended more on ordinary drainage than on exceptional wood chemistry. Builders learned to slope surfaces. They placed joints where water could escape. They allowed air to circulate around vulnerable timber. Modern building science gives precise names to many of these details, but the underlying principle is simple. Durable construction shortens the time wood spends in the combination of moisture, oxygen, and temperature that allows decay fungi to remain active. A dry path through a structure can be as important as the species chosen for the frame. Yet some wooden objects cannot be protected this way. Fence posts must enter the soil. Railway ties sit close to wet ground. Docks, bridges, and waterfront structures can remain exposed to water for long periods. In those places, drying alone cannot provide enough protection. The wood itself has to be made less suitable for the organisms trying to consume it. Some wooden structures have to remain in places where moisture cannot be designed away. A fence post buried in soil may stay damp around its base for much of the year. Railway ties, retaining walls, docks, and utility poles can face the same basic problem. In these settings, wood preservation often depends on placing protective chemicals inside the material itself. Pressure-treated lumber is designed for exactly that purpose. The treatment adds compounds that make the wood less suitable for fungi, termites, and other organisms that would otherwise use it as food. Modern systems commonly rely on copper-based preservatives, often combined with other chemicals that improve protection against particular organisms. Copper is especially useful because many fungi are sensitive to it. The exact preservative depends on the intended use, local regulations, and the type of wood being treated. The treatment process usually begins inside a large sealed cylinder. Bundles of lumber are loaded into the chamber, and a vacuum may first remove some air from the wood's open spaces. A liquid preservative is then introduced. Pressure is applied so the solution is pushed deeper into pathways that once carried water through the living tree. These include cell cavities, pits, and vessels in wood species where those roots remain open enough. Afterward, another vacuum may remove excess liquid from the surface. The goal is to leave useful amounts of preservative inside the wood, rather than simply coating the outside. Two measurements become important here. Penetration describes how deeply the preservative reaches. Retention describes how much protective chemical remains in a given volume of wood. Both affect long-term performance. A treatment that reaches only a thin outer shell may leave deeper material vulnerable if the wood is later cut, drilled, cracked, or badly weathered. A deeper treatment can provide more protection, where decay organisms might eventually enter. Different exposure conditions require different treatment levels. Lumber intended for an above-ground deck railing faces a milder environment than a post buried directly in wet soil. Ground contact material is therefore treated to a standard intended for more severe and persistent exposure. The wood species itself still matters. Sapwood usually accepts preservative more easily because many of its original water pathways remain relatively open. Hardwood can be much harder to penetrate. Closed pits, tyloses, extractives, and other features formed during hardwood development can block liquid movement. Some species are so resistant to treatment that manufacturers make small cuts in the surface before pressure treating them. This process is called incising. The cuts create extra entry points that help preservative move farther into the wood. Douglas fir is one species where incising has often been used because its heartwood can be difficult to treat deeply. Pressure treatment also has a long history. For much of the 20th century, one widely used preservative was chromated copper arsenate, usually shortened to CCA. It combined chromium, copper, and arsenic compounds to protect wood from decay fungi and insects. CCA-treated lumber became common in decks, playground equipment, fences, and other outdoor structures. Beginning in the early 2000s, its use was restricted from many residential consumer applications in North America. Other preservative systems became much more common for household lumber. Modern treated wood can last far longer than untreated vulnerable wood in the same environment, but its lifespan is still controlled by exposure. Repeated wetting, deep cracks, poor construction details, and untreated internal zones can eventually create opportunities for decay. Preservation therefore works best when chemical treatment and good design support each other. The underlying idea closely resembles the natural protection found in durable heartwood. A living cedar or teak tree deposits defensive chemicals during growth. Pressure treatment introduces a different set of protective compounds after the tree has been cut. Both approaches change what fungi encounter when they enter the wood. Modern materials science can push the idea further. Instead of placing protective chemicals into existing spaces, wood can be altered so that the cell walls themselves absorb less water and behave differently at the molecular level. Pressure treatment works by placing protective substances into wood. Material modification goes deeper by changing the wood itself. One approach uses heat. Thermally modified wood is heated far beyond the temperatures used for ordinary kiln drying. Commercial systems often work somewhere between roughly 160 and more than 200 degrees Celsius, depending on the species and process. At those temperatures, parts of the wood begin to change chemically. Hemicelluloses are especially sensitive. These shorter carbohydrate molecules help make up the cell wall and contain chemical groups that readily attract water. As heat alters some of those molecules, the finished wood becomes less able to take up moisture from humid air. That change affects the way the material behaves. Wood normally swells as bound water enters its cell walls and shrinks again as that water leaves. Thermally modified wood usually goes through smaller changes in size because its cell walls hold less moisture under the same surrounding conditions. A deck board or exterior cladding panel made from modified wood may therefore remain more dimensionally stable as humidity rises and falls. Lower moisture also makes the material less favorable to many decay fungi. The cell wall spends less time containing the amount of water needed for fungal chemistry to operate efficiently. Heat treatment can also create trade-offs. The same temperatures that alter hemicelluloses can change other parts of the cell wall. If treatment becomes intense enough, certain mechanical properties may decline. The wood can become more brittle, and some forms of bending or impact strength can decrease. Manufacturers therefore have to balance durability and stability against the strength needed for the final use. A second approach changes the wood through a chemical process called acetylation. Researchers began experimenting with acetylated wood more than a century ago. Work at the United States Forest Products Laboratory began in the 1940s and helped establish how strongly the process could improve dimensional stability and resistance to decay. Acetylation targets chemical groups inside cellulose, hemicelluloses, and lignin called hydroxyl groups. A hydroxyl group contains an oxygen atom bonded to a hydrogen atom. These groups attract water molecules and help explain why untreated wood readily gains moisture from humid air. During acetylation, many accessible hydroxyl groups are converted into groups containing acetyl molecules. The basic wood structure remains recognizable, but the chemistry inside its cell walls changes. Fewer sites are available to hold bound water. As a result, acetylated wood usually reaches a lower moisture content than untreated wood exposed to the same humidity. It also swells and shrinks less. Those changes can be substantial enough to improve the stability of window frames, doors, exterior cladding, and other products exposed to repeated changes in weather. The effect on fungi is closely connected to the cell wall. Decay organisms need more than liquid water sitting in a crack. Their enzymes and reactive chemicals have to operate within the microscopic structure of the wood. Reducing the amount of water held inside that structure can make movement and chemical reactions more difficult. Researchers have also proposed that acetylation changes the size of microscopic spaces available inside the cell wall, which may restrict some of the molecules fungi use during decay. The full mechanism is still being studied. Lower cell wall moisture appears to be a major part of the explanation, while changes in molecular transport and accessibility may add further protection. Thermal modification and acetylation therefore reach the same general problem by different routes. Heat alters portions of the original wood chemistry. Acetylation deliberately replaces water-attracting chemical groups with less water-friendly ones. Both can make the cell wall less hospitable to organisms that depend on moisture to break it apart. Neither treatment makes wood permanent. A modified board placed in severe ground contact can still face years of wetting, fungi, insects, and physical wear. Field tests remain important because laboratory resistance cannot capture every condition found outdoors. Still, these methods show how far wood preservation has progressed. A material grown by a tree can now be changed at the scale of individual chemical groups. Some of the oldest surviving wood known to archaeology reached extraordinary ages without any such treatment. Its preservation came from a very different source. Cold water, buried sediment, and low oxygen sometimes created conditions where ordinary decay slowed enough for timber to outlast entire civilizations. Deep inside wet soil, wood can enter a very different kind of aging process. The change happens slowly enough that structures built more than 2,000 years ago can still leave recognizable timbers behind. One of the clearest examples lies at Biskupin in present-day Poland. The site stands in a low, marshy landscape beside Lake Biskupin. During the early Iron Age, around the 8th century BCE, people built a fortified settlement there using large quantities of timber. Rows of wooden houses stood behind defensive walls, with streets and other structures also made from wood. Over time, much of the settlement disappeared beneath wet ground. The site remained hidden until 1933, when unusually low water levels helped expose ancient wooden remains. Archaeological excavation began the following year. What researchers found was remarkable. Timbers that had been cut more than 2,500 years earlier were still present in the saturated soil. Their survival came largely from the conditions that developed around them after burial. Water filled spaces in the soil and greatly reduced the movement of oxygen. Microorganisms near the surface consumed much of the oxygen that did arrive. Deeper down, the environment became increasingly oxygen poor. That restricted many of the brown rot and white rot fungi that normally break wood apart quickly. Cool temperatures and the absence of sunlight also slowed several biological and chemical processes. The result was a burial environment where timber could remain recognizable for an extraordinary length of time. Decay continued at a much slower pace. Certain bacteria are especially important in waterlogged archaeological wood. A group commonly called erosion bacteria can attack the cell wall even when oxygen levels are extremely low. They often begin near the hollow center of a wood cell and gradually erode portions of the surrounding wall. Cellulose and hemicelluloses are particularly vulnerable. As these carbohydrate materials disappear, the more lignin-rich parts of the cell wall can remain for longer periods. Soft rot fungi may also be present where slightly more oxygen is available. Some produce tiny cavities inside particular layers of the wood cell wall. Viewed through a microscope, an ancient timber can therefore reveal damage that would be impossible to judge from its outer shape. The beam may still have square edges. A tool mark made by a builder centuries ago may remain visible. Inside the material, much of the original carbohydrate framework can already be missing. Water gradually occupies spaces created by that loss. This can make archaeological wood contain far more water than sound modern timber. In severely degraded material, the mass of water held inside the structure can even greatly exceed the mass of the remaining dry wood. The timber survives partly because its weakened microscopic framework remains supported while saturated. This creates an important difference between shape and strength. A preserved post does not need to retain the mechanical properties it had when someone first placed it into the ground. Its outer form can remain recognizable, while individual cell walls become porous and fragile. Biskupin also demonstrates how sensitive that preservation can be to environmental change. Modern researchers have monitored groundwater around the site because lowering the water table can allow more oxygen to enter previously saturated soil. That shift can encourage organisms capable of faster decay. A groundwater monitoring system was established there in 1991, and measures were later taken to help maintain wet conditions around buried remains. The water that makes excavation difficult can therefore be part of what has protected the timber for centuries. Archaeological wood carries two histories at once. Its visible shape records the people who cut and used it. Its microscopic structure records the long period spent beneath water and sediment, where bacteria slowly removed material one cell wall at a time. That hidden loss becomes especially dramatic when the surviving object is much larger than a post or plank. Entire wooden ships have spent centuries beneath the sea, while their timbers followed the same slow path, preserving their form as their internal structure quietly weakened. A large wooden ship can remain recognizable on the seabed long after the people who built it have disappeared from history. Its beams may still hold their original shape. Joints can remain visible, and pieces of the hull may still look surprisingly solid. Inside those timbers, however, centuries of slow microbial activity can leave a very different structure. The Nanhai No. 1 shipwreck offers an unusually clear example. This merchant vessel sailed during China's Southern Song dynasty, which lasted from 1127 to 1279. It sank in the South China Sea roughly 8 centuries ago, while carrying goods associated with the maritime trade routes linking China with ports farther west. The wreck was discovered off Guangdong province in 1987. After years of investigation, the entire surviving wreck was raised from the seabed in December of 2007 and transferred to the Maritime Silk Road Museum in Yangjiang. Researchers have examined timber from the ship with light microscopes and electron microscopes. Samples came from several tree species, including Mason pine and Fujian cypress. Some pieces retained remarkably complete cell walls. Others showed moderate erosion, while a smaller number had been severely degraded by bacteria. The surrounding seabed helped create that uneven preservation. Much of the wreck had been covered by silt. Water filled the sediment, and oxygen became scarce beneath its surface. That environment restricted many of the fungi that would normally consume exposed timber quickly. Bacteria capable of functioning with very little oxygen continued working inside the wood. Two important types found in waterlogged archaeological timber are erosion bacteria and tunneling bacteria. Erosion bacteria gradually attack parts of the cell wall from surfaces bordering the hollow interior of the cell. Tunneling bacteria can create narrow channels through the wall itself. Under a microscope, severe bacterial damage can leave some cells with only a thin framework remaining. The arrangement of the original wood may still be recognizable even after much of its internal material has been removed. Cellulose and hemicelluloses tend to suffer heavily during prolonged waterlogged decay. More lignin-rich portions can persist longer. This creates the same strange condition seen in buried archaeological wood, now on the scale of an ocean-going vessel. The outside can preserve geometry, while the inside loses much of the chemistry that once provided strength. Nanhai No. 1 is especially useful because different pieces experience different amounts of erosion, despite spending roughly the same 8 centuries underwater. The particular wood species mattered. Local conditions around individual timbers mattered as well. How deeply a beam was buried in sediment could change its oxygen exposure and the microorganisms able to reach it. A much deeper shipwreck in the same sea shows how far these conditions can be pushed. On the northwestern continental slope of the South China Sea, researchers discovered wreck sites dating to the Hongji period of the Ming dynasty, between 1488 and 1505. The second site lies roughly 150 kilometers southeast of Sanya, near the Shisha Islands. Its timber rests at a depth of about 1,500 meters, where the water remains close to 3 degrees Celsius. Large wooden logs found there can appear dark and hard even after more than 5 centuries. Chemical and microscopic examination tells a more complicated story. Parts of the carbohydrate structure have deteriorated, while lignin-rich material has survived more successfully. Microorganisms associated with surrounding seawater and sediment have also been detected within the waterlogged wood. Cold temperature slows biological activity at that depth. Low oxygen inside buried areas can restrict familiar decay fungi further. The enormous pressure of deep water changes the physical environment as well. Although preservation still depends on the wood species, local sediment, and microbial community rather than depth alone. A timber can therefore spend 500 or 800 years underwater and still preserve the outline of the object a carpenter shaped. Its microscopic condition may tell a much less reassuring story. Cell walls can become thinner. Carbohydrate material can disappear while water occupies the spaces left behind. Much of the remaining strength may depend on a fragile structure that has been saturated for centuries. That becomes especially important when the timber is finally removed from the environment that preserved it. Once the supporting water begins to leave those weakened microscopic spaces, an ancient piece of wood can change far more quickly than it did during hundreds of years beneath the sea. Once waterlogged archaeological wood is brought into open air, the conditions around it can change within hours. For timber that has spent centuries underwater, ordinary drying can be dangerous. Sound modern wood contains cell walls strong enough to hold their shape as moisture leaves. Severely degraded archaeological wood may have already lost much of its cellulose and hemicellulose. Water fills many of the microscopic spaces left behind. In that condition, the water becomes part of what helps the weakened structure keep its shape. As evaporation begins, liquid retreats through tiny pores and cell cavities. Surface tension creates forces along the curved surfaces of the remaining water. Inside strong wood, those forces are usually manageable. Inside damaged archaeological timber, they can pull fragile cell walls inward. The result may be severe shrinkage, cracking, warping, or complete collapse. A beam that survived underwater for 800 years can therefore suffer major damage during a relatively short period of uncontrolled drying. Conservators try to prevent that change before too much water is removed. One widely used material is polyethylene glycol, usually shortened to PEG. Polyethylene glycol is a water-soluble polymer available in different molecular sizes. When waterlogged wood is soaked in a PEG solution, the polymer can gradually move into damaged areas of the material. As treatment continues, some of the spaces once occupied almost entirely by water become filled or supported by PEG. The goal is to reinforce the weakened microscopic structure before drying begins. This approach has been used on some of the world's best-known preserved ships. The Swedish warship Vasa which sank in 1628 and was raised in 1961, received years of polyethylene glycol treatment after recovery. The English warship Mary Rose, which sank in 1545 and was raised in 1982, also required decades of conservation involving polyethylene glycol and carefully controlled drying. Large artifacts demand patience because treatment chemicals may need years to move through thick timbers. Drying itself can also be controlled. One method is freeze drying. The treated wood is frozen, turning much of its remaining water into ice. Pressure is then reduced inside a chamber. Under those conditions, ice can pass directly into water vapor without first becoming liquid. This process is called sublimation. Avoiding a prolonged liquid stage reduces some of the capillary forces that can pull fragile wood cells together during ordinary evaporation. Conservators can measure whether these methods are working with increasingly precise tools. Three-dimensional scanning records the outer shape of an artifact before, during, and after treatment. Changes of only a few millimeters can reveal shrinkage or distortion. Microcomputed tomography works somewhat like a medical CT scan on a much smaller scale. X-rays are used to build three-dimensional images of the internal structure without cutting the object apart. These scans can reveal cracks, voids, dense treatment material, and areas where weakened cell walls remain. Conservation methods themselves have also changed as older treatments revealed unexpected problems. During the late 19th and early 20th centuries, some Scandinavian archaeological wood was treated with alum, a group of aluminum-containing salts. The method could help stabilize wet wood during drying and was used on important artifacts, including objects from Viking Age excavations. Over many decades, researchers discovered serious chemical consequences in some alum-treated wood. Acidic conditions developed inside the material. Cellulose broke down further, and portions of the wood became extremely fragile. Some objects that had initially appeared successfully preserved later required new conservation work. That history changed the way conservators think about treatment. Saving archaeological wood is an ongoing materials science problem. The water content has to be understood. The chemistry of previous treatments matters. Changes may continue for decades after an artifact enters a museum. An ancient timber can therefore be most vulnerable after its long period of burial has already ended. Humans value the preserved shape because it connects directly to a ship, building, tool, or settlement from another time. In a living forest, the same disappearance would serve a completely different purpose. There, the gradual destruction of dead wood returns stored material to an ecosystem that depends on decay. A fallen trunk in a forest is entering a very different kind of useful life. Its wood may no longer carry water to leaves or hold a crown above the ground, but the material inside it still contains a large amount of stored carbon. Roughly half of the dry mass of wood is carbon, although the exact proportion varies among species. That carbon originally came from the atmosphere. During photosynthesis, a tree takes in carbon dioxide through its leaves. Using energy from sunlight, it builds sugars from carbon dioxide and water. Those sugars become raw material for growth. Over time, some of that carbon is incorporated into cellulose, hemicelluloses, lignin, and many smaller compounds inside the trunk. A large tree can therefore hold years or centuries of accumulated carbon in woody tissue. Once the tree falls, that material does not immediately return to the soil or atmosphere. Much of it is locked inside cell walls that very few organisms can digest efficiently. This is where wood decay fungi become essential. The brown rot and white rot fungi that can weaken a damp house beam perform a necessary job in forests. Their enzymes and reactive chemicals open woody tissue that would otherwise remain difficult for most organisms to use. Brown rot fungi are especially important in many forests dominated by conifers. They rapidly attack cellulose and hemicelluloses while leaving behind much of the altered lignin. That remaining material can become chemically resistant and may persist in soil for long periods. White rot fungi follow a different route. Their ability to break down large amounts of lignin gives them access to one of the toughest carbon-rich materials produced by plants. Without organisms with that chemistry, lignin-rich wood would accumulate much more slowly into forms other decomposers could use. As fungi digest the log, part of its carbon is released through respiration. Fungal cells use carbon compounds for energy and produce carbon dioxide as a waste product, much as animals do during respiration. Other carbon becomes incorporated into fungal tissue. That tissue can then be eaten by insects, mites, springtails, and many other small forest organisms. A fallen log also changes physically as decay continues. Its surface softens. Cracks widen and pieces begin to separate. Water can collect in the damaged wood more easily than it did when the trunk was sound. This creates a damp habitat that may remain cooler and more humid than the exposed forest floor nearby. Ecologists often call fallen trunks and large branches coarse woody debris. The name sounds simple, but this material can become an important part of a forest habitat. Beetle larvae may tunnel beneath loosened bark. Mosses and seedlings can establish themselves on old logs. Small animals can shelter beneath them, while fungal networks continue moving through the remaining wood. As the structure breaks apart, fragments mix gradually with the surrounding soil. Mineral nutrients contained in the tree become available again through decomposition and weathering. Nitrogen, phosphorus, calcium, potassium, and other elements can eventually move into soil organisms or be taken up by living plants. The speed of this process varies enormously. A small branch in a warm, wet forest may disappear relatively quickly. A massive trunk in a cool or dry environment can remain recognizable for many decades. Some large pieces of dead wood can persist for centuries when the species is durable and conditions slow decomposition. Diameter matters because a thick log takes longer to break down throughout its full volume. Position matters as well. Wood lying against moist soil experiences different conditions from a standing dead trunk exposed to moving air. Climate changes the activity of fungi and other decomposers by controlling temperature and moisture. This means dead wood acts as a temporary carbon store whose lifetime depends on the same variables that influence wooden buildings. Moisture, oxygen, species chemistry, temperature, and fungal access all matter. The difference is in what success means. For a house, preserving the beam is the goal. In a forest, decomposition allows old wood to become part of living systems again. The fungi that seem destructive in a building are performing one of the processes that keeps forests from filling indefinitely with undecomposed trunks. That biological machinery is deeply established across ecosystems. For wood engineers, the realistic challenge is therefore to manage decay rather than imagine a material that can permanently escape it. The useful question becomes how long a piece of wood can remain strong when species, treatment, design, moisture, and time are all working together. By this point, the useful measure of durability becomes more precise than simply asking whether a species resists rot. Engineers often think instead about service life. Service life is the amount of time a material can continue doing its intended job before deterioration becomes unacceptable. For a wooden beam, that may mean remaining strong enough to carry a load. For exterior siding, it may mean staying structurally sound through decades of rain and drying. Predicting that lifespan requires bringing many of the earlier pieces together. The species establishes the basic anatomy and chemistry. Sapwood and heartwood may begin with very different levels of natural protection. Extractives can slow fungi, while open vessels or trachytes influence how deeply water enters. Temperature affects fungal metabolism, and oxygen determines which decomposers can remain active. Construction details control how quickly wet wood can dry. Preservatives and chemical modification can add further protection. Cracks, fastener holes, damaged coatings, or freshly cut surfaces may create new roots into timber that was previously well protected. Researchers therefore test wood under several kinds of conditions. Laboratory decay tests provide control. Samples can be cut to the same dimensions, maintained at carefully chosen temperatures and moisture levels, and exposed to a known fungal species. Scientists can then measure changes in mass, chemistry, or strength. These experiments make direct comparisons much easier. Outdoor exposure adds the complexity of real weather. One of the harsher methods is the ground contact stake test. Wooden stakes are placed partly into soil and left there for years. The buried zone remains damp for long periods and stays in close contact with fungi and other organisms. Rainfall varies naturally. Temperatures change with the seasons, and the wood experiences repeated wetting and drying. That makes ground contact a demanding test of long-term durability. Modified wood has shown why several measurements are needed. In Greece, researchers followed highly acetylated radiata pine stakes through 10 years of ground contact exposure. Radiata pine is a commercially important species, originally native to a small part of coastal California and nearby islands, although it is now grown extensively in plantations in countries such as New Zealand and Chile. The acetylated samples resisted visible fungal decay remarkably well. After 10 years, some highly modified stakes showed little or no obvious fungal damage on their surfaces. Mechanical testing revealed a more complicated result. Certain measurements of stiffness and bending strength had declined even when visual decay remained very limited. A piece of wood can therefore look sound while changes important to structural performance are already occurring. That matters far beyond experimental stakes. A hidden beam inside a wall may appear normal through a small inspection opening. Painted exterior wood can retain a smooth surface while damage develops beneath it. Visual appearance provides useful information, but it cannot reveal every change happening inside the cell wall. Modern monitoring can add another layer. Small moisture sensors can be installed inside wooden walls, roofs, or structural members. They record whether the material repeatedly enters moisture conditions favorable to decay. Engineers can combine those measurements with hygrothermal models. Hygrothermal simply refers to the combined movement of heat and moisture through a material or building assembly. A computer model can estimate how rain, indoor humidity, outdoor temperature, ventilation, and construction layers influence moisture over months or years. These tools help identify situations where timber may spend too much time above decay-relevant moisture levels, even when the problem remains hidden. Laboratory tests still cannot reproduce every event that may occur during 50 years outdoors. Field tests cannot control every variable as neatly as a laboratory can. For that reason, modern durability research combines fungal biology with chemistry, microscopy, mechanical testing, weather exposure, and computer modeling. Each method reveals a different part of the same aging process. Long-lasting wood usually succeeds because several opportunities for decay have been reduced at once. A durable species may be paired with good drainage. Pressure treatment can protect vulnerable timber, while a roof or flashing limits how often it becomes wet. Modified wood may absorb less moisture, while careful construction prevents water from collecting in exposed joints. Service life grows from those interacting protections. The two pieces of wood from the beginning can now be understood in the same way. Their different futures begin in their cells and chemistry, then continue through every drop of water, fungal filament, temperature change, and human decision that follows. A fence post standing at the edge of a yard brings almost every part of this story together. Near the soil line, its wood may stay damp for long periods after rain. Oxygen can still reach that shallow zone. Temperatures may remain mild for much of the year, and fungal spores are already present in the surrounding environment. If the post contains vulnerable sapwood, the conditions become even more favorable. Hyphae can spread through the wood's old transport pathways and begin digesting the cell walls from within. Brown rot fungi may rapidly damage cellulose and hemicelluloses. White rot fungi can attack lignin as well. Soft rot fungi may become important in wetter conditions. As enough structural material disappears, the post begins to lose strength. The change may begin below the surface long before the wood finally feels soft beneath a hand. An old beam beneath a dry roof follows a very different path. Its species still matters. Hardwood chemistry, grain direction, and the proportion of sapwood can influence its natural resistance. But a much simpler condition may explain most of its survival. The beam stayed dry. A sound roof kept rain away. Air movement allowed small amounts of moisture to escape. If the wood remained below roughly 20% moisture content for most of its life, decay fungi rarely had the water they needed for sustained attack. That beam might remain useful for several centuries, even if its species would decay quickly when placed in damp soil. Naturally durable hardwood adds another layer of protection. Western red cedar contains compounds that interfere with fungal growth. Teak, redwood, and black locust use different mixtures of extractives to create their own forms of resistance. Those chemicals were placed into older wood while the tree was still alive. The same piece of timber may also contain blocked pits, tyloses, or other anatomical features that slow the movement of liquid through it. Human treatment can extend those defenses. Pressure-treated lumber carries preservatives into accessible cell spaces. Thermal modification changes parts of the wood chemistry through heat. Acetylation alters water-attracting groups within the cell wall, reducing how much bound water the material holds. Each method interferes with part of the decay process. The archaeological timber buried beneath waterlogged sediment takes another route entirely. Its cell walls may contain little of the natural durability found in cedar or teak. Continuous saturation keeps the wood wet, yet oxygen becomes scarce beneath mud or deep water. Many familiar decay fungi slow dramatically. Bacteria and soft rot organisms can continue working, sometimes for centuries, gradually removing cellulose-rich material, while leaving more lignin-rich structure behind. The object may preserve its original outline even as water fills spaces created by microscopic loss. Once excavated, that same waterlogged timber can shrink or collapse if it dries too quickly. Conservators may use polyethylene glycol, freeze-drying, scanning, and other methods to support a structure that survived centuries in conditions very different from those inside a museum. In a forest, decay plays yet another role. A fallen trunk contains carbon that the tree originally pulled from atmospheric carbon dioxide through photosynthesis. Fungi unlock that material by breaking down wood polymers that most organisms cannot digest efficiently. The same chemistry that damages a damp house beam helps return carbon and nutrients to forest food webs and soils. Every piece of wood, therefore, carries a lifespan shaped by several interacting conditions. Secondary xylem provides the original structure. Cellulose, hemicelluloses, and lignin determine what decomposers must dismantle. Hardwood formation changes the chemistry. Extractives can slow attack. Grain and permeability influence where water and organisms can travel. Moisture, oxygen, and temperature decide whether fungal metabolism can continue. Design and treatment can interrupt that process for years or centuries. There is no single clock hidden inside wood. A piece may disappear quickly when the conditions for decay remain favorable. Another can remain beneath a dry roof for generations. Cold, oxygen-poor sediment can preserve recognizable timber far longer still. The material begins with the tree, but its eventual lifespan is created by everything that happens around it.